Hello everyone, and welcome. Today, we're tackling a classic fluid dynamics problem involving water flowing through a horizontal pipe, which is essential for understanding many real-world engineering systems. Step 1. Visualizing the setup. Imagine a horizontal pipe. It starts wide at section 1 and then narrows down to section 2. We have water flowing from the wider part to the narrower part. You'd visualize arrows indicating flow direction and pressure gauges at both sections. This setup helps us understand how the pressure changes as the water speeds up due to the constriction. Step 2. Identifying our knowns. We're given the density of water, that is, ρ, as 1,000 kilograms per cubic meter. This value is constant throughout the pipe. At section 1, we know the pipe diameter, d1, is 8.0 centimeters. The average speed of the water, V1, is 2.0 meters per second, and the gauge pressure, P1, is 250 kilopascals. At section 2, the pipe diameter, D2, contracts to 4.0 centimeters. Our goal is to find the gauge pressure at section 2, which we'll call P2. Step 3, the principles we'll use. First, we'll use the equation of continuity, A1 V1 equals A2 V2. This principle states that for an incompressible fluid, the volume flow rate must be constant. Here, A represents the cross-sectional area and V is the fluid speed. Since area is proportional to the square of the diameter, this can be written as d1 squared V1 equals d2 squared V2. Second, we'll apply Bernoulli's principle. P1 plus 1/2 ρ V1 squared plus ρ GH1 equals P2 plus 1/2 ρ V2 squared plus ρ GH2. This principle relates pressure, speed, and height in a flowing fluid. Since our pipe is horizontal, H1 equals H2, so the ρ GH terms cancel out. This simplifies Bernoulli's equation to P1 plus 1/2 ρ V1 squared equals P2 plus 1/2 ρ V2 squared. Step 4. Solving for pressure. Our main objective is to find P2. To do this, we first need to determine the speed of the water at section 2, V2. We'll use the continuity equation for this. V2 equals V1 over D2 squared. Substitute the given values. V2 equals 2.0 meters per second times the right 2 centimeters. Notice how the diameter units cancel out. V2 equals 2.0 meters per second times 2 equals 8.0 meters per second. Now that we have V2, we can use the simplified Bernoulli's principle to solve for P2. P2 equals P1 plus 1/2 ρ V1 squared minus V2 squared. Substitute the numerical values, remembering to convert P1 from kilopascals to pascals. P1 equals 250 kilopascals equals 250 times 10,000 pascals. P2 equals 250 times 10,000 pascals plus 1/2 ρ equals 2.0 meters per second. P2 equals 250,000 plus 500, 4 minus 64. P2 equals 250,000 minus 3,000 equals 220,000. Converting back to kilopascals, P2 equals 220 kilopascals. Step 5. Checking our answer. Our calculated gauge pressure at section 2 is 220 kilopascals. This value is less than the initial pressure of 250 kilopascals at section 1. This result is consistent with Bernoulli's principle. As the pipe narrows, the water must speed up to maintain the constant volume flow rate from continuity. According to Bernoulli's principle, for a horizontal pipe, an increase in fluid speed must correspond to a decrease in its static pressure to conserve energy. Our values align perfectly with this physical expectation. Step 6. What does this mean? We found that the gauge pressure at section 2 is 220 kilopascals. This problem beautifully demonstrates the Venturi effect. As an incompressible fluid flows through a constricted section of a pipe, its speed increases, and its static pressure simultaneously decreases. Understanding these principles is fundamental for designing efficient piping systems, analyzing water distribution networks, and even studying phenomena like blood flow in arteries and veins. Step 7. Additional insights. A crucial insight from this problem is the relationship between diameter and speed. Although the pipe diameter was halved, the water's speed didn't just double, it quadrupled. This is because the cross-sectional area, which dictates the flow speed through the continuity equation, depends on the diameter squared. This non-linear relationship means small changes in pipe diameter can lead to very significant changes in fluid speed and, consequently, pressure. Step 8. Summary and broader context. In summary, we first used the principle of continuity to determine how the water's speed changes as it enters the narrower section of the pipe. Then, by applying Bernoulli's principle, which is a statement of energy conservation for fluids, we calculated the resulting pressure at that narrower section. This problem highlights the interconnectedness of fluid speed, pressure, and pipe dimensions, reinforcing key concepts in fluid dynamics that are essential for understanding everything from aerodynamics to hydrodynamics. Thank you for joining this session. If you found this explanation helpful, please give it a like, subscribe for more physics and mathematics content, and share it with your friends. Feel free to leave any questions or comments below. And if you have a specific physics problem you'd like me to solve in a future video, consider donating to the channel. Each month, a few donor-requested problems will be selected and solved right here.